All right, let's continue with some blade characteristics. So we did talk about, in your choice, there's blade thickness, the airfoil shape, the width, number of blades, yep, diameter, pitch. Let me put this over here. And can I zoom out? Can I zoom out with this? And put this over here. And you have this in your packet, this page. All right. So this is spinning to the right. You have the hub, you got the blades, you got the blade root, the trailing edge, all right, which is this part here. This is the part that is spinning here. This is the part that hits flat, essentially. And as this is spinning out of the page this way, you create thrust that way. All right, I'll show you the thrust equation in a minute. And again, why are the propellers designed like they are? They have to be curved out towards the end because it's spinning faster on the outside. You want to have equal kind of forces so it doesn't shaft, just snap in half, vibrate too much. Okay. This is kind of what we're talking about. The top line here, top picture. This is kind of the airfoil shape. And then this is how it's curved out. All right. This is important right here. So down at the bottom, airfoil section, this is kind of a typical wing shape. All right. For the most part, though, you get, you see how these are just kind of saying, like positive pressure, negative pressure. As it spins around, you have positive and negative pressure. Okay. You see these huge spikes in these airfoil shapes, but you don't see them too much in this. They'd rather go with this, okay, because it won't cause cavitation as frequent. That you could actually drop your pressure too much. It's going to cavitate the water, then you now have many explosions that could hurt the prop over time. So that's why we kind of go with this other shape right here, okay, for prop designs. So you have the different types. There's skew, there's rake, and there's cupped type props. So skew. And that's this picture on the right. And the advantage here is the water enters sequentially, therefore reduces vibrations. What does that mean? I'll tell you here in a second. So with the skew, if you notice, compared to even this one, this kind of goes up and around, kind of like it kind of skews from meaning this is the center line here. It's slightly different on this right-hand side than it is on this left-hand side, and it's more of a circle oval shape. So as the water, as it's spinning, the water kind of touches the prop up here first, and then it kind of hits that point. So it kind of touches, doesn't touch this whole surface all at once as it's spinning. It's kind of more of an oval skew shape. That's definitely what you want. You kind of want it to slice through instead of hitting like a paddle. All right. That's skew. Now rake, you see on the left. This one basically is just kind of shifted to the left of this line right here, which is kind of the center line down here. They usually use these in tight situations, okay? So you can increase the area by tilting it like that to get into tight situations. And then I believe on the next page, I think, is cupped. Nope, I didn't have cupped. But I'll tell you what those are. Basically, at the end of these tips out here, it kind of curves up a little bit, like kind of like a cup would. Okay? Those, they're at the blade tip. And usually reduces cavitation. Oh, sorry. At the blade tip, and what it does is it adds area and helps reduce cavitation. So you can have a prop that's skewed with cup. Just kind of curls up at the end. That would significantly help reduce cavitation. Those, there really isn't a much theoretical say, okay, it's going to reduce cavitation. It's more of, let's try it and see what happens kind of thing. All right? For now, there is. Okay, so let's go through an example of how to find pitch, all right, which is the way that blade is angled towards the outside up. Okay, and pitch is also defined as, if you have like a 21-inch pitch on a prop, how many inches it would actually move, okay, as it spins one revolution. So here's some givens. Oh, I'll do it over here to save some space. So the WL, if you remember, was the waterline length, 30 feet. We're going to go at 18 knots, and we have 12,700 pounds. Yeah, 30 feet. Yep. For knots, yep. Or Kate, yep. Yep. So first we're going to find SHP. If you remember, knots times the pounds over 1/2 divided by this. This might be a new equation for you. And this C is kind of a constant for different types of boats. So for a passenger boat, the constant is 150. There's kind of like a class. Use 150 for these types of boats, yeah. Most of it was through experiments. So you get about 182 horsepower. Okay? We're going to take this number. We're going to divide by 0.75 to make it like a, we don't always want to run at 100% RPM for the motor. We're going to run at 75%. Okay? So now, this new SHP is 242 horsepower. Right? You don't want to always be cranked full max all the time. You want to be at, in this case, 75%. It's typical. So we're going to pick an engine that gives us 240 horsepower and delivers 3,000 RPM. And it's going to use a 2.4 to 1 gearbox, so reduction gear. What's that? We're going to, so basically what it's saying is 1250, I think that's what you said, right? RPMs are going to go to the shaft. Yeah. Okay, so this is right now, okay, we picked this engine, we got this going. What we need to do is, for an ideal case, this is the ideal correction to find pitch. And we're going to use different ways. We're going to use the charts later on to get a more appropriate ideal solution. But let's just keep this in mind. So what we're going to do, yeah, that's fine for right now. We have to fix it. We can fix it later. Pitch equals basically the speed over the RPM. So we have roughly, what did we say, 18? And 1250 for RPM. Can someone plug that in their calculator? I'm changing this slightly just to give an idea. Oh, shoot. We want it in inches, so let's convert this. Let's see, what do I have here? So this is 18 nautical mile per hour. I'm going to convert it to 101.3. Then we're going to multiply by 12 inches and 1 foot. And then we're going to divide by 1250 RPMs. So that conversion converts it to feet per minute. Okay? So this is feet per minute instead of knots. Okay? I think that conversion, whoops, this 101.3 does all that. Converts to nautical mile per hour, which is knots, 2 feet per minute. Okay. And sorry, go ahead and put that in there. So 18 times 101.3 times 12 divided by 1250. 17.5 inches? Rough, is that what you got? Anybody else check that?
Yeah.
Just to double check. Yeah, from knots to feet per minute, and you get that to inches per minute, I guess. So this is saying that one revolution should move 17.5 inches. We know it doesn't, right? And that's kind of what we call slip. We know that it doesn't. We get slip because there's other forces factored in. This is a theoretical idea of what's going to happen. Okay? Usually what they do is they get this rough idea, and then they say, okay, which one can we buy? Can we buy 18 or 17? Put it on there and see what we get. Usually they measure RPMs, make sure they're not going over the rating for the engine, and double check their speed, make sure they're still getting the speed. And that's what I'm going to have you guys. Okay. Finding diameter. I could probably show you this in the Excel file. So, and there's something we missed. I'll just kind of go through it. And there's a couple other equations that we can write down. All right. So if you brought your computers, if not, just watch. But let's build this Excel file. We'll do it together. I have it done. And there might be some corrections that we'll do within the Excel file, but it gives you an idea of what we need to do. Okay. So if you do have your computers, if not, there's two over there. So two people want to go over there. Actually, I do have another laptop right there. No. Yeah, go ahead and write this out. We'll do it together. Does anybody want a laptop? Or you can take notes and do it later. And if you want to hop on those computers over there, you can too. So this one, there might be some corrections that I'm going to show you that we do. But for the most part, by the time you're done, you'll be able to use this to kind of size a prop. Okay? And hopefully, I want to do it with the props that I got. And we might have to call the manufacturer to get some props. I don't know if we have. You might be able to just use the prop curve that we have just to make sure you understand how to do it. They don't have them online. We might have to find them if they do. So this is just some random example that actually the book goes through, and I kind of went through it. So we'll start with length overall, and then the length of the water line, the beam overall, beam water line, hull draft, okay, the maximum draft. You ever heard of long tons? Not tons. Like metric tons? It's just another way of like measuring like force or weight. I put displacement as pounds. Max prop diameter to fit within the existing aperture. Shaft center line, and then the knot. So my goal is to kind of do this with both of them. Take some measurements. Hopefully figure out how much it weighs, how much we put in there. So the beam is just like the width. We could have a picture. I'll get back there. Oh, that's not the one I wanted. Is it this one? Yeah. So just to get an idea of what we're looking at, the draft, where the water line is, all the way to the bottom. Okay. And the beam is the width. Okay. And then the beam water line, if you notice, this is thicker, but not where the water is. Okay. For probably smaller boats, they're probably all the same. Sorry, there you go. So the max prop diameter, that's important, right? You have to know that. Especially in boats that aren't like outboard, they're inboard, and just have like a shaft going out. Because if you measure and you get a 75-inch out, then it's going to be perfect. Put it on there, it's going to rub, right? And then you're going to notice when we go down below that if you did by the book, I actually put the formula number in there. And there might be some more that we're going to add in notes. And we'll write these down as we go. It's formula 5.5. None of these formulas that I'm going to show you that I didn't show you yet, are still good. I just wanted to get started on this. Most likely we'll probably finish this Wednesday. It would be nice to have a boat here. I forget these are only 50-minute classes. They go pretty fast. You're an hour 15. Yeah. I think it's just the aperture. Doesn't want to stay there. There. Still see it okay, everyone? Maybe a little smaller. And what we're going to do is we'll do this line and show you what it is, and then I'll write the formula down. Okay? Some of these are the formulas that you need to see. If I do that, okay, hold on, I'm going to try something. Bear with me. It does the big thing, okay. If I go there, is that okay? Because now what I'm going to do is put this down here. And I'll write the equation as we go. About those apples. Okay, so the minimum diameter acceptable is what they call a D prop min. That is 4.07 times BWL times HD raised to the 0.5. Bless you. So, I'm gonna get my charger. Let me do this and scroll up. How come it's not, there you go.
Need that 12-foot charger.
Right.
Huh, I wonder who pushes this? Because they're not supposed to. It's too close to the, maybe Haskins is.
I was gonna say you use the board a lot.
Yeah.
I just loaded up.
I mean, he could push it, but he's got to push it back because we're breaking the code. There. All right. So this is the actual minimum diameter based on your beam water line and your draft. Okay? Next. DL ratio. If you remember what that was. Actually, it's probably easier if I do this. You know what I'm going to do? I'll just write it on the board. 2.22. So go ahead and write that in. So the DL ratio, that's what we're working on, right? Is, what do we have? Displacement? Divided by 0.01 times WL to the third. We're going to use that in this one. Okay? Or that one, we'll see that. We'll use that later. So this SL ratio this should be V12, which is our speed, knots, divided by the square root of WL.
You write WL from the length water line? That would be correct.
Yep, yes, yep. Length of the water line, yep. Everyone good?
So overall length of your boat, that's not, that may or may not be in contact with the water.
Yeah, all of it might not be, yep.
Okay, and
Yep.
LWL is what's directly in contact.
Exactly touching the water,
So
and
you
then
have like that
lengthwise.
overhanging lip side, that's like your overall
Yeah,
length
usually,
of
and you'll see,
part.
even with my boat, because the front curves up like this, like halfway down is where it actually is actually touching the
And
water.
that's where you do like
That's where you do
the
WL.
LOA is gonna be the whole length, you
Yeah.
go up the curve.
Yes. Yep. Okay, and then SHP, which is the next line. That's, I'm pretty sure I gave you that. That is rearranged from the shaft HP, which I'll give you this way, you can just say rearranged. They use this SL ratio, and there should be a 10 point something in there, right? So, yeah, that's what I was gonna do. This one is B17. Actually. Come on. Can you read that?
Yeah.
So B17 times B9 raised to the 1/3, and then divide by 10.665. And it's from this formula here. You get that in the email.
So this is like building a sheet, so you can just put values
Yep.
whatever you want.
Yep, that's what I'm having you do.
Which one's this one?
What's that?
What value is that?
That's all right.
So it's SL ratio?
Yeah.
This? This is SHP.
That's the HP.
Yep.
Okay.
Which is right there.
Yeah.
Yep.
We'll go back to Firestone.
Yep. I almost need 3 computers.
I was gonna say, you just need 2 projectors, in general, that have 2 monitors.
Yeah.
It wouldn't be a bad thing. Put it in space.
So you should get 858. Does everyone get 858? Back there? Kyle, how you doing? Did you get 858?
Oh, okay. You go back up to the SHP.
Yeah. Let's make sure everyone's caught up. So where you want?
SHP.
Yeah. Let me zoom in. You got it?
You just didn't, she didn't put a gap between 13 and 14. Like you didn't put a gap between
Oh,
the two
okay.
lists.
Yep.
So like what you tried to do B17, it was the same row that she was writing in.
Okay. So you should get 858. Then, if you, I
A lot of
don't,
horsepower. Oh, never mind. It's just that
you
one
can
time.
almost put these values in and figure out how I did it. Okay? Bearing loss, that's the loss, kind of bearing loss and exhaust back pressure. Okay? So we're doing 3% bearing loss. What we're doing is we're working our way back. We have SHP, given these ratios that we took from above, to figure out what our actual brake horsepower, engine power that we're going to need. Okay? So the bearing loss is 3%. And then before the duty cycle, we just basically need to increase that by 3%, right? So I took SHP and I just divided by 1 minus 0.03, okay? That is the quick way in Excel to do that.
You multiply it by the 0.3.
Or 1.03. So I'm dividing by 90.97.
Yep.
Then here is a duty cycle for continuous operation. All right. So they're usually the motors that you're trying to get for your brake horsepower are on an average duty cycle. So we're just going to take a typical value that's always running 85% of that. Okay. We're going to increase it by 15%. That's where this value is. Okay.
That's final carry.
This is the final one. Yep. Yep.
So it's almost like reverse factor safety.
Yeah, that's kind of what we're doing. Yep. Yep. Yep.
I don't know if it's so much for reverse factor safety, factor. I don't know if it's so much for reverse factor safety, it's factor safety itself.
Yeah,
Or-
because you solved it first and then added in after.
Yeah, you're adding friction, you're adding losses, and then you're adding kind of a continuous friction loss over time.
You are right, though, it is straight up factor safety.
Yep.
Yeah. Just looking at it the backwards way. I guess.
So,
Yeah.
yeah, times 1.03, that's another correction factor that we use.
Yeah, you're adding to it.
We're just kind of bumping it up a little bit more.
Takes you down whenever.
Exactly.
But in case of this, if I can get one, I have to put the one with rock.
Yeah, right.
So again, this 1.03, they just kind of said, okay, this is bump it up a little bit more. So is everyone up to that point right there?
Yeah.
1,040.
Over 30 feet.
Is that what the
So we're doing, we're gonna,
Really?
you're gonna do over here.
Or if it's
Kind of fill it into the right. Yeah, we'll finish this
as
Wednesday.
long as it's not like truck load, like, you know,
Right,
right.
very, very clearly not.
Sorry.
Is there questions? Make sense?
Personal watercraft over 30 feet.
It's not really, it's just
Personal water.
losses, duty cycle, and a little bit of factor.
Yeah, but it's over 30 feet.
When you say personal watercraft, like, what-
Okay, now what we did is we're gonna pick an engine. So you have to select an engine. And this one, we just picked the Cummins KTA 38M. And it gives us some parameters. Okay? So we got max HP, so horsepower, which is 1,045. You got a max RPM of 1,950.
Well, a lot of those that still have to.
Probably right.
100-foot boat? Yeah.
Probably. Yeah.
I know.
You would hope.
Yeah.
I know a couple
If you're running a
30-foot
single
boats that run
engine.
2 engines, let alone a 100-foot boat running a single engine, single Cummins.
Yep. So you would do the same thing if it's dual. There is I think down below where there's a correction factor for 2 props. So you just know, okay, you could buy, you know you need half of this. Yep.
So when one breaks, they have
So this,
Get the whole joystick drive.
what we're looking at now in this our boat safe HP is we're comparing it before the duty cycle. Okay. So this takes this max HP and that's the duty cycle correction factor. Sorry, make sure everyone got that. Everyone get 888? We just take the max HP and we multiply it by the duty cycle. And then this next one is kind of looking at the 3% bearing loss. And what do we get for that? Yep.
Default, what do we get for shaft across?
This one that I just had?
Yeah.
Yeah. We're just looking at the 3% above. Okay. All right, let's write this formula down. And let me zoom in up here for you so you can do that. Oh, what was that number? Hold on, I'll zoom back out. 5.3. Right there. So this formula right here is the prop diameter as a function of RPM and SHP. So I'll write it like this, and then that I think we're just changing it. Imagine being the PhD student and all these formulas. One PhD student is probably one of these formulas. That's what their full degree was. So this again is RPM, shaft, and the diameter of the prop. Okay. But what we did is we rearranged it, right, to solve for SHP based on what diameter?
RPM
Yes. Yeah. Oh, sorry. Yeah. Solving for RPM based on our maximum diameter that we assumed up here is 74 inches. Okay. Yeah. It's huge. So again, we're using SHP, the diameter, our max diameter, to figure out what that RPM is that we're going to need at the prop. That's again based on the max HP and some bearing losses. So again, let me zoom up here to make sure you get it. So if you notice, we took parameters for the boat that's sitting in the water. We figured out some max values that we needed. We found some ratios. We figured out kind of our SHP that we needed. We back calculated with friction losses, some corrections to figure out the actual brake horsepower we need inside the boat. Then we looked that up in the manufacturer. We found an engine. And then we're kind of now going back the other way to find SHP. We are using our biggest diameter first to find the RPMs that we need to figure out, really, in a sense, what this gear reduction would be. Okay? So we know the max RPM from the motor, and we now know the RPMs at the shaft. We can then figure out what gear reduction we need inside that engine. Okay? And you should get 5.3. 5.43, sorry. So using the RPMs that we now have at the prop, the SHP, then we can then figure out exactly how we can actually size this better, right? Because right now, we're only assuming maximum diameter. And we want to know if that's good efficiency, how much thrust we're going to get. Okay? So that's what, and we'll finish this on Wednesday. That's what these next ones are. Do a first attempt. And then you figure out, okay, what's happening, and is there cavitation? If there is, then you do another attempt. Okay? Then you again check for cavitation. And then finally, you make sure things are going to work. Okay? So I'm going to show you these parameters here, if you notice. The number of blades, what this value is, how you find these on the chart, and some other equations that we use. Okay? So really, we've initiated the process of what do we need to know at this shaft, at the top? RPMs, SHP. Now, what we need to do is pick a blade type. Is it cup? Is it oval? Is it, what's the thickness? These are what these are. The number of blades. Then there's more equations. And we're going to use the charts that are in the packet to figure this out. Okay? So the goal then Wednesday is to finish this, make sure you understand how to do this. And then if there's any extra time, we'll think about what we need to do for the boat that I bring in on Friday. I'll bring my boat on Friday. Okay?
How would we be able to measure the water level and stuff?
We either take it,
Put it in the water,
put it
and
in the
then
water, and do it.
somebody get in the water and measure it.
Measure it.
If somebody's going for a swim, or
Or there is another technique that you could try. I don't know. We could try it and then take that in the water. There's an example in the back of this book how to do it out there in the park. I don't know how well that would work, but
and the weight, which like
the weight. So maybe if we get scales, I have to figure out. We'll figure out a way to weigh this thing. I wanted to take the U-Haul. We'll take the boat off, because the boat's pretty light. Few people can lift the boat off. What? The dump, yeah. Maybe on my way out, if it's open, I'll pull in. And figure it out. Or if we have 3 scales and 3 2x4s, we can line it up and put it on the 2x4s.
so you like 3 actual like
Weight
weighing
scales.
yourself scales.
Yeah. Yeah. And just weigh the wood. So okay.
Well, you can zero with the wood on it.